All right, good morning. Let's get started. Sorry for the late start. We're going to talk about probability again, probability models today. Last probability lecture we talked about classification models using probabilistic mechanisms for classification. And today we're going to use probabilistic models purely for density estimation. So we're going to fit probability distributions to our data. I feel I should warn you, this is probably the most mathematical lecture in the series. I feel I should warn you for two reasons. First, for those of you who are sort of extrapolating in your head and thinking we're about halfway, if this is how bad it gets, how bad is it going to be in 2 weeks? Don't think of it like that. Think of it as the peak of a hill. We've reached the peak of the hill and now we're gently rolling down the other side. Because all of the stuff we've learned so far, we're now going to use to make things simpler for ourselves after this lecture. And the second thing is, with all these mathematical derivations, what I want to achieve with these things is, I don't necessarily want you to be able to do them yourself or even follow along all the steps, but it's important to see that this kind of stuff exists, how the basics of it works, and basically to know how it works in case you ever need it. So if you ever go deeper into machine learning, you will need this kind of stuff. If you're worried about the exam, have a look at the homework. Anything difficult that we're going to ask you to do in the exam will be practiced in the homework. If it's not in the homework, you will not have to be able to do it quite so technically as I do it here. That's a promise. All right. So I hope I've scared you enough. Let's go to the plan, right away to the plan. So the only thing we're going to talk about today is maximum likelihood estimation. Likelihood, which is this frequentist principle that I told you about in the last lecture, where you choose the parameters for your model that maximize the likelihood of your data. And then we're first going to apply that to 4 different models based on the normal distribution, or the Gaussian. Because that's quite an intimidating sort of mathematical object, I'll try and go through it quite slowly and show you exactly how these Gaussians work before we start fitting maximum likelihood stuff. And then we'll end up on a model called the mixture of Gaussians, which is a little bit difficult to fit. It's very powerful, but difficult to fit using maximum likelihood. And then in the second half, therefore, we are going to look at the expectation maximization algorithm, which is a way of fitting Gaussian mixture models. We'll start with a sort of intuitive approach, hopefully. And then we'll look at it a little bit more formally. So that's the plan. Let's start with this maximum likelihood thing. Let's start with a simple example. Let's say you have 2 coins. One coin is bent and one coin is straight. So the straight coin lands heads 50% of the time and tails 50% of the heads 50% of the time. And oh yeah, it's like this, sorry. So the straight coin lands heads 50% of the time and tails 50% of the time. The bent coin lands heads about 4 and 5 times and tails about 4 and 5 times. And we ask a friend to pick a random coin without showing us and flip it 12 times and show us what the results are. And this is what comes out. It goes heads, tails, heads, heads, and so on. So there are more heads in this sequence than tails. Oh yeah, and obviously the question for us is, which coin did he use? Did he use the bent coin or the straight coin to get this result? So there are more heads than tails. So in some sense, you might say, well, it's probably the bent coin. On the other hand, if we only had a straight coin and you had this outcome, you wouldn't be massively baffled. You wouldn't say that would never happen with a normal coin. So the question is, which coin did he use and which coin should we guess? If we had to guess one of the coins. So this is kind of an analogy of model selection the kind of model selection that we do in machine learning. So the coins are our model space. We have just two models. And the coin flips are our observed data. And we have to fit a model to this observed data. What the maximum likelihood principle says is, hold on, is it here somewhere? No. What the maximum likelihood principle says is, given this data and some coins, so we have two models, bent and straight, pick the model for which the probability of the data is the highest. So we calculate the probability of the data given that the coin is bent and given that the coin is straight, and the coin that gave us the highest probability, the highest likelihood, probability of the data given the model, we choose. So we have a model in some model space. We search the whole model space, ideally, and then we search it for the model that gives the highest probability to the data. So that's a sort of pretty straightforward way. Sometimes it goes wrong, this principle, the maximum likelihood principle. We won't look into that today. In many cases, it's a pretty good principle to go with. So just to finish the coin example, we can assume that every coin flip is independent. So the probability of the whole sequence is just the probability of the individual events multiplied by each other. So for the bent coin, we just multiply 4 or 5 for every heads and 1 5 for every tails. So we get about 3 zeros and then 2 6 8. And for the straight coin, we just multiply 12 1/2 because both events have probability 1/2. And it turns out that the probabilities are quite close, but ultimately we should prefer the bent coin a little bit. So that's maximum likelihood fitting, right? Which is quite similar to what we've been doing already. So the likelihood, or it's usually the logarithm of the likelihood, mostly because the logarithm is a little bit easier to work with. We get these likelihoods are quite complicated formulas. So if you take the logarithm, the formula usually gets a lot simpler. So we usually take the logarithm because the logarithm looks like that, which is what we call a monotonic function. So if I take some output, I pass it through the logarithm, the highs are going to get a lot less higher, and the lows are going to stay roughly the same. But all in all, the maxima and the minima won't change. It won't change where the function reaches its highest point. That's called so a monotonic function is a function that keeps going up and up and up, which means that the log likelihood has its maximum where the likelihood also has its maximum. So we might as well maximize the log likelihood. So that's what we maximize to fit a probability model to our data. And we had this loss function we've been dealing with, which is what we minimize to fit a machine learning model to the data. So basically, they're the same thing. And we'll see later that these things start looking a lot alike. So basically, if we take the negative log likelihood, then we're minimizing, then we can treat it like a loss function. So if we ever have to optimize probability models in like a deep learning system, where the assumption is that you're minimizing, then you just take the negative log likelihood. So let's have a look at these normal distributions. These are the 4 that we're going to look at. Let's write them down. 1D normal, the regression model, the ND normal distribution, the multivariate normal distribution, and then finally the mixture of Gaussians. Incidentally, if you wonder where the name Gaussian comes from, it comes from this man called Carl Friedrich Gauss, who sort of invented these distributions. He's probably one of the top 3 mathematicians in history, so that's a good name to know. So let's start with the normal distribution. I think you've all seen it before. It has a mean and a variance or a standard deviation. To parameterize it, the mean is where it peaks, and the variance defines, as it were, the scale of the distribution. And it's sort of why the normal distribution is so popular, I think, is because it has this definite scale. I think I talked about this earlier as well, but if something is normally distributed, like people's height, then there is some uncertainty. You don't exactly know what people's height is. But it's never going to be less than half a meter, and it's never going to be more than 4 meters. So you have this definite scale where you can be really, really sure that the results are going to be there, even though you have some variance. And that's not true for other distributions like income, where if you just keep increasing the population, you will see the income multiply by 10 and then by 10 again, the sort of highest income you can see within a population. But normal distributions have this definite scale, which is why they're also good, for instance, to measure measurement errors. So if you have a measurement error, you're not exactly sure about the outcome of your measurement, but you're pretty sure it's within a certain range of inaccuracy. Here's a question I always ask when I talk about normal distributions and continuous distributions. So we see a red point and a blue point here. And the question I always ask is, which point has the highest probability under this distribution that I've drawn here? It's a trick question. I think it's a little bit early for trick questions, but any idea why it's a trick question? Why this is not, why obviously you would think the red point has the highest probability, because that's where the line is highest. Why doesn't the red point have the highest probability? They're about 0. I think you've seen this question before, right? Yeah. So this is not a probability function. This is a probability density function, and that's an important distinction. All the individual events that come out of this distribution that we see when we sample from this distribution, they're all 0. So if these are heights, for instance, the probability that somebody's height is exactly 2 meters is 0. And the only things that have probability are intervals. So I can assign some probability to the event that somebody has a height between 1.5 meters and 2 meters. But as that interval gets smaller and smaller and smaller, no matter how likely the outcome, the probability always goes to 0. So individual events have a probability density, and by integrating over that probability density, we get a probability. We won't do any integration, but it's important to understand the distinction. So let's look at the normal distribution, which looks like this. This is the 1D, the 1D normal distribution, one-dimensional normal distribution. So we have a single scalar x and 2 parameters, a mean and a variance, and then this massive imposing formula. So I thought the first thing I do is take you through this formula and show you where it comes from, because everything you see here does a fairly simple job. So I hope I can sort of take make it a little bit less imposing by going through it step by step. So let's start by the sort of fundamental thing we want from her, the fundamental requirement that we want from this normal distribution, which is that it has this definite scale. And in order to give something a definite scale, we want the tails of the distribution at the very least to decay exponentially, which means that if you take a fixed step, the probability is multiplied by something smaller than 1. So if you take something like the blue line here, e to the power of x, well, I can't do it for e in my head, but let's say we take 2 to the power of minus x. Then at 1 we have probability density 1/2. At 2 we have 1/4. At 3 we have 1/8. So at 10 we're at about 1 in 1,000. At 20 we're at about 1 in a million. At 30 we're at 1 in a billion, and so on. So you take a relatively small number of steps, and the probability density decays exponentially, right? And that's what we like, because then we have a definite range where we're almost certain that all of the probability, is. So you get that if you do e to the power of minus x, but we actually make it decay even faster by doing e to the power of minus x squared, because when we do that, the function has a nice inflection point, by which I mean there's a point around 1.7 here somewhere where the function stops decaying faster and faster and faster, and starts decaying slower and slower and slower. So here it's the rate of decay is increasing, and here the rate of decay is decreasing. So it has a real point where this switch happens, and that's the point we can use to take as a sort of canonical element of our range, this inflection point. And it has another nice property that it has this little bell on the top so that we don't get a hard angle once we hit 1. So let's, sorry, I'm new presenter, I'm still getting used to it. And the square also means that it's also defined over negative numbers. So if we look at the whole number range, we see that it's symmetric because the square gets rid of the negative sign. So we get a nice symmetric bell curve. And here we have these inflection points, and between the inflection points is where the curve, where most of the mass is. I can't call it probability mass yet because it's not a normalized function yet. But this, basically, this simple function already gives us most of what we want from the probability density function of the normal distribution. All we have to do now is make sure it behaves like a probability function and move it around a bit. So it lands exactly on the place where we want it to land. So let's look at these inflection points first. Here you can see if you draw the derivative of this line, the inflection points are where the derivative peaks. That's where the rate of decay switches from faster and faster to slower and slower. So these are the points where we put most of our probability mass. And the first thing we do is we rescale the function so that these inflection points hit -1 and +1. Because that's sort of neat. Right now they're at a sort of around 1.7, which is a bit messy. And turns out that if you just put a 1/2 in front of the x here before the square, then they hit -1 and +1. So we rescale it a bit. Then we want to control this range. Now that we have it between these nice numbers, basically we say if we just want this to be between -2 and 2, we just scale it by 2. Which is called the standard deviation. So we just work that into the formula. So if we take this 1/2 multiplier and we divide it by how much we want the function to grow, then we can control the size of this scale. And of course we want to be able to put the peak where the probability function peaks. We also want to put that wherever we like. So in order to move the function around, we can also move the axis around. So instead of moving the function forward, we can move the input backward. So we take this input and we just subtract however far we want to move the function forward. So that's the mean. If we want the mean to be at 2, we subtract 2 from x. So now we have a nice probability function. All we need to do now is make sure that the probability of the whole number line, so the area under the entire curve, sums to 1, which you can do. I mean, I wouldn't exactly know, be able to explain to you how this is done, but let's say somebody smart did it and worked out what the value is if you integrate this entire function between -∞ and +∞. Something pops out, and we just divide this whole thing by whatever that is, so that the thing sums to 1. And this is whatever that is. So you divide it by the square root of 2 pi times the standard deviation. And that gives you the one-dimensional normal distribution. A bit of notation first. So if we talk about the probability density of a point under a given normal distribution with a given mean and variance, we write it like this, x given those parameters. And if we talk about a random variable distributed according to a distribution or sampled from a distribution, we talk about this. So now, the other way around, this maximum likelihood thing. If we are given some data, let's say I see some grades, and I want to fit a normal distribution to those grades, The question is, what is the maximum likelihood estimate of our parameters? So we have two parameters, mu and sigma, the standard deviation, sigma squared. And for every value of those two parameters, we get some likelihood over our data. So I've plotted it here. It looks exactly like a loss surface, except the other way around. So the brightest points now are the highest points. And all we want to do with the maximum likelihood criterion is find the highest point in this space. So let's work it out for the mean. This is the only one I'm working out. The rest you can sort of look up. So we want to find the theta. Theta is just a symbol that we use for all the parameters that we're interested in, such that the logarithm of the data given the parameters, of the probability of the data given the parameters, is maximized. And since we assume in almost all of these cases that our data is independently drawn, the probability over the whole data set is the product of the individual probabilities. So we just take this product here, and a product inside a logarithm is a sum when you take it outside of the logarithm. So this is our objective, to maximize the theta, sorry, to maximize the sum of the logarithm of the probabilities for theta. And then we fill in this specific case for the 1D Gaussian, univariate Gaussian. So we're maximizing over mu and sigma, sum of the logarithms of this massive function that we've just been looking at. If we take the logarithm in, we have the product of this bit times this bit. So we take that out of the logarithm, then we get the logarithm of this bit plus the logarithm of this bit. And on the second bit, the logarithm cancels out against the exponential. So we get the logarithm of this normalizing constant, or this normalizing part of the function, minus the bit in the exponent. And that's what we're trying to maximize. So it should come as no surprise to you that we're going to take the derivative, because we want to find maximum. We're going to take the derivative of this thing with respect to mu, because we're only doing mu at the moment. So the derivative of the log likelihood with respect to mu, which is the derivative of that thing with respect to mu, this whole normalizing part of the function that just we can ignore because mu doesn't occur there. So we're only interested in the second part, which gives us this, and the 1 over the minus 1/2 times 1 over the standard deviation is independent of mu, is a constant independent of mu, so we can work it out of the derivative and out of the sum, because it's also independent of x, which we're summing over. So the derivative is starting to simplify quite a lot. And the derivative of this, if you apply the chain rule, is just 2 times x minus mu. So the 2 we can cancel out with the 1/2 in front. So we end up with this as the derivative. And so far, we've always been pretty happy to just leave it here and use gradient descent to find our optimum. But in a lot of these cases, there's actually an analytical solution, right? So the optimum is where the derivative is equal to 0. So for just this time, let's just set the let's just work that out. So we set the derivative equal to 0. Derivative is the product of two things, this bit with the standard deviation and the sum. So in order for that to be 0, either one of them has to be 0. It can't be the thing in front because the standard deviation is always bigger than 0. So this thing in front is never 0. So it has to be this sum is 0 if the whole thing is going to be 0. So we know that this is true. We have this mu inside the sum, which doesn't actually depend on the thing we're summing over, so we can work that mu out of the sum, which just works out as n different mu's. Basically, we have n terms if there are n points in our data. So we work out these n mu's, which gives us, or these n minus mu's, I should say, which gives us minus mu n plus the sum over x. And if we rearrange this, solve it for mu, we get that mu is the good old-fashioned mean that we already know. So actually, the maximum likelihood estimator for the mean of a normal distribution is just the mean of your data. And you can do the same thing for the standard deviation. and for all of these functions, almost all of these functions. But the mean is the only one I'll work through entirely, like this. So that's our 1D normal distribution. And before we move to the multivariate, the ND normal distribution, let's have a look at something I sort of mentioned earlier, that when you talk about least squares regression, that actually there is an assumption of normality. In some ways, there's an assumption of normality in there. So let's see what I meant by that. Basically, what you can do, you can think of this model as a probability distribution. You can say, we assume that our data was generated by using this, this line, but adding a little bit of noise. So X is sampled from some probability distribution that we don't know. And then we compute the Y belonging to X by first transforming it by this function, this linear function, and then adding a little bit of Gaussian noise. Here's what that looks like. So we start with X, which is, we don't know how X is distributed. But then we transform X by multiplying by W and adding B, which is just the standard linear transformation. And then we add another random variable, E, which is distributed according to a normal distribution, which is centered at 0 and has some variance that we also don't know. So given some point X, we find the point on the line, and we add a little bit of random noise, Gaussian random noise. That means if we want to maximize the likelihood of these parameters of our linear model, the parameters of the line, given some data, Y and X, that this is our maximum likelihood objective. We want to maximize the probability of Y given X, W, and B. So if we fill that in, that looks like this. So the probability over Y is a normal distribution, and the mean of that normal distribution is the result of our linear function. So we fill it in, this big scary function. We work out the logarithm. And since we're taking the argmax, we can just ignore this thing because it's constant with respect to W and B. So now the normalizing thing just disappears. And in fact, this probably disappears as well. There we go. So this sigma, this standard deviation that we picked for the normal distribution, disappears as well. It doesn't matter for the values of W and B. So now we're maximizing minus 1/2 over this value, which is the same as minimizing the negative of this thing. So we flip it around and minimize it. And what we end up with is just our least squares objective function, our least squares loss function. This is just the output of our linear model minus the target squared and then summed over the whole data with a little 1/2 in front. That doesn't really matter for the minimization. So this is why I say least squares regression is in some sense assuming a normal distribution. Or maybe the other way around, if you assume a normal distribution and you fit the maximum likelihood objective, you end up with least squares regression. Now the multivariate distribution, which is again, oh, we're there already, sorry, which is again a very scary function. So let's go through it step by step, and you'll see that it's sort of built up roughly the same way as the univariate normal distribution. So now our mean is a vector, and our variance has become a covariance matrix. And we get this big scary function. So the basic principle is the same. We want a function that decays squared in this squared exponential way. But instead of decaying just in two directions, it now decays in every direction. So we have a mean, which we'll put at the origin for now, the center of the distribution. And the further we get from the origin, the smaller our probability density gets in a squared exponential decay. So we just take the distance to the origin and we put this in this squared exponential function. So the norm of x is the distance to the origin. If you take the square of a norm of a function, that's equal to just taking the dot product of the function with itself, right? Because the dot, this is the definition of the norm. So if you take the square of this, the square and the square root cancel out against each other. And then we do this normalizing trick with the 1/2 again, so that the what's now an inflection circle, so all the points where the rate of decay switches around form a circle in this space around the origin. And then we make that circle the unit circle, so it crosses the point 1 and -1 by just putting a 1/2 in front. So this unit circle now, for this distribution, contains most of the probability mass. That's our sort of characteristic scale for this function. And this time we normalize first. So now we work out whatever the total volume under the curve is, and we divide by that, put it out in front. So that all we need to do now is figure out how to move this thing around in space, how to take this unit circle and move it around in space and stretch it around to fit our data. And we're going to use a trick that I talked about earlier already. We are going to take this function and apply a linear transformation. So we said that any linear transformation of this bell curve is a normal distribution. So if we have a point, so we have this is already, it's normalized, so this is already the standard normal distribution. It has its mean at 0 and variance 1 in every direction. So we apply a linear transformation to that shape. We're going to transform that shape. So here's a standard normal distribution with some points sampled from that normal distribution. We apply some linear transformation defined by the matrix A and the vector t. So what we see is that the mean point gets moved around, and this unit circle that captures most of the probability mass gets sort of stretched out in that direction. And now if you want to know the probability density of a particular point, let's say the blue point under this distribution, essentially what we can do is we can transform it back and work out the probability density under this function and apply a small correction, and then we get the probability density of this point under this function. So we're going to transform the point back with the reverse of this transformation to find the probability density. So if Px is the probability density of this point under the standard normal distribution, then what we find is that Px of the point transformed backwards is essentially the right probability density, except that this transformation, as you can see here, it's rather stretched out, it's rather blown up this probability density. It's blown up the amount of probability that is captured by this characteristic ellipse in this case, that's inside this point. So we need to correct for that. This blow up, we need to correct for that by working out how much this ellipse blows up, how much this transformation blows up the volume inside the orange ellipse, and then divide by that, so that the function sums to 1 again. And how much a linear transformation blows up its space, that's called the determinant of a matrix. So it's entirely determined by the matrix A, and the determinant of that matrix gives us the rate by which, is a single number, gives us the rate by which the volume of space is sort of blown up, how much more surface area is in this ellipse than in this one. So we divide by that. This is how the determinant of A is written. We divide by that, and then we get the probability density of this point under the transformed Gaussian. So if we combine these two facts, this is the transformation, and this is where we were our definition for the standard normal Gaussian, we can apply this trick to this function. Oh, animations are off again. So here we divide by a, and here we do the inverse of a and mu minus the x. So sorry, I've messed this up slightly here, but mu, we equate mu with t, and we equate sigma with a times at. We'll see later why that is. So mu is just the same as t. It's the same as this transformation. It's the translation part of this transformation. So if we work this out, two things are happening. On the left side, well, it turns out if you look at the properties of the determinant, it turns out that if you take the determinant of A times its transpose, that's the same as the square of the determinant. So if you take the square root of that, then this is the same thing as this. And on the right side, we can work this transpose into the brackets. And working a transpose into the brackets looks like this. You flip around the bits inside the bracket, and you apply the transpose to each. So that's what we're doing there. Which brings us here, which gives us these two a minus 1s next to each other. And then if you look up the properties of the matrix inverse and the matrix transpose, it turns out you're allowed to do this. You're allowed to work the matrix inverse, the minus 1, outside and the transpose inside, which gives us this, which shows us why this A times AT is equal to the covariance matrix. And that's basically where this function comes from. It looks like this. Before we move to the Gaussian mixture model, just a quick trick. If you don't want to compute the likelihood, but you want to sample a number from one of these distributions, that's relatively simple, probably more simple than computing the likelihood. So we'll take this one as given. So if you have, if you want to sample from a standard univariate standard normal distribution, there's functions to do that. It's called a Box-Muller transform if you're interested. But let's take that as read. Let's say we have some function that can do that for us. Well, we sort of already know how to then turn that into a sample from any other distribution by transforming it by the parameters. So if you want to sample from a non-standard univariate normal distribution with a given mean and sigma, we just sample some x from the standard normal distribution, we multiply it by the variance, and we add the mean, and that gives us a sample from this distribution. So that's pretty simple. If we want to sample from a multivariate normal Gaussian, so it's a multivariate Gaussian, but it has its mean at 0, variance 1 in every direction. What we can just do is take a bunch of samples from the univariate standard normal distribution and stick them in a vector, and that's a sample from the multivariate standard normal distribution. So that's very easy. And then again, if we want to sample from a multivariate, from any multivariate normal distribution with a given mean and sigma, we just work out what this linear transformation is by decomposing the sigma. We sample from the standard distribution, and we apply the transformation, and that gives us a sample from the desired distribution. All right. So that's the ND normal. So I'll just before the break, I'll just set up the Gaussian mixture model, which we're mostly going to talk about after the break, but just to set things up. These are the grades from, I think, 2 years ago for this course. And they look a little bit normally distributed, but not that normally distributed, right? Looks more like they have one peak here, and one peak here. which is usually a sign that you have sort of three different populations in your student, in your general population, three different clusters, three different types of people. So let's say the people who like it, people who didn't like it but really need a grade, and the people who thought, ah, screw it, I'll do it next year. So it's good to decompose your population in that way. So a single normal distribution is not going to give you 3 peaks. What you need for that is multiple normal distributions. So let's say we want 3 peaks. What we can do is we can define 3 separate normal distributions, and we can give each a weight. So let's do that. We have a red, a green, and a blue normal distribution here. We're just in 1D for now. And we give each a weight by which we scale the likelihood. Not the likelihood, the probability density function. And then we can sum these scaled functions. They will sum to 1 because the weights sum to 1. So if we sum these, the resulting value will give us a probability density function that is not at all normal. It has 3 peaks, 3 modes. And it can fit the data in this very non-normal way. And that makes of this black line, the probability model of this black line, is defined as the sum of these 3 weighted probability densities. It's a Gaussian mixture model. So in order to figure out, to fit this to our data, to figure out what the best Gaussian mixture model is for our data, the maximum likelihood objective would say, take these 3 sets of parameters, these 3 means, 3 sigmas, and 3 weights, and work out which ones maximize the probability of your data, or the log probability density of your data, I should say. So if you're panicking and think, well, is he going to now work out the derivative of this and set that equal to 0, don't worry. Because we can work out the gradient of this, but we can't set it equal to 0. Or, I mean, we can set it equal to 0 and do what we like, but we cannot rewrite that into a neat closed form solution. And the gradient doesn't look that nice either, because what you see here is a sum inside a logarithm. And that's sort of our worst nightmare, because the sum inside of a logarithm, you're sort of stuck. You can't really work it outside of the logarithm, because the sum is part of the probability density function. So we can't simplify this. So even if we take the gradient, and it's useful in some cases, it doesn't look very nice. So we don't usually do that. Instead, we use something called the expectation maximization algorithm. And that's what I'll talk about after the break. So let's take 15 minutes, and we'll digest this, and we'll catch up after that. All right, find your seat. And let's get started with the expectation maximization algorithm. Before we move into expectation maximization, let's review an algorithm that I talked about in the first lecture, called k-means. I hope you remember this. This is a clustering algorithm. Just to go through it quickly, so we have a data set, cloud of points, and we want to cluster these into 3 clusters. The way the k-means algorithm works is that we pick 3 arbitrary means, a blue mean, a blue mean, a green mean, and a red mean. We put them somewhere in space, doesn't really matter where, and then we color all the points by which mean they are closest to, like this. And then we recompute the means from these colored points. So we take the mean of all the blue points, the mean of all the green points, and the mean of all the red points. So we get some new means, and then we iterate. We recolor the points, we recompute the means, recolor the points, and so on, and we see that it converges to a local optimum, but it converges to quite a nice clustering of our data. So the EM algorithm that we're going to talk about is kind of an extension of this idea, where we look at these components. So we have multiple multivariate normal distributions that we consider responsible for our data. And we do a kind of coloring in this way, assigning points to components. And we fit the distributions to those subsets of the data that we've assigned, and then we iterate this principle. But first, a little bit of context. So this Gaussian mixture model is essentially a hidden variable model. So we have a process that we imagine is how our data came to be. And that process consists of sampling a random value z, and from using that random value z, sampling a value x. In our case, we have these components with their component weights. So from this distribution on the components, we sample one of the components. Let's say it's a rare case, so we sample the red component. And then from that red normal distribution, we sample a number x, and that's our x. And the problem with the hidden variable model is that we only observe the x's. We don't observe the z's. So we only see this, but all of these three components have some probability density here. So x could have come from any of them, but in this case it came from the red one. So what we need to do in some way is to complete the data. We need to infer what these z values were, or a distribution on these z values, given the x values, and then we can compute the likelihood. So if you're a bit familiar with statistics and with the probability theory, I should say, you might ask, can we just marginalize out this set? Just write down the distribution on the joint distribution on x and z, and then sum out over all possible z's. And then we just get the marginal distribution on x. And yes, you can do that. And that would be this sort of ideal way of doing it. The problem is you get this sum. And this Z is essentially, let's say you have two components to make it easier, then this Z is 1 bit of information per component per x, right? It's 1, 0, or 1 per component per x that tells you which component you chose. So overall x's, you get, if you have n x's, you get 2 to the power of n different assignments of points to components. And this is one of those exponential functions that grows very quickly. So even if you have just 30 points in your data set, which is very small for a data set, and just 2 components, you already have 1 billion terms to sum over. So it's a huge, huge sum that you can never compute. So we need something better. Well, we've already seen that we can't work out an analytical solution. We can work out the gradient, but we can't set it equal to 0 and write it around to get an analytical solution for the parameters. So we use the EM algorithm, which works from this basic insight. We cannot do this marginalization because we cannot optimize for theta and z together. So theta are the theta is just one sort of symbol that stands for all the parameters of our model together. So inside this theta are our component weights, the component means, and the component sigmas. And z are which component generated each data point. So if we know, let's assume for a second, that we knew exactly what the correct model parameters were, then we could easily compute the probability distribution over which z generated which point, or over which component generated which point. And if we knew exactly which component generated which point, then we would have complete data, and then we could easily fit a maximum likelihood model to that. But we can't do both together, so what we do is we iterate both steps. We start with some random guess for our components. We just pick a bunch of random, let's say we have 2 components. We pick 2 normal distributions somewhere in space, some random mean, some random sigma. Then we assign soft responsibilities to each point. So each component takes some responsibility for each point, proportional to how much probability density it assigns to that point. And then we weight the data by these soft responsibilities. And on that weighted data, we fit new components. I have some pictures here to make it more clear. So we have some data and we have two arbitrary components. And we then, instead of coloring each point red or blue like we did in the k-means algorithm, we color it a little bit blue and a little bit red. And the more probability density it gets from the blue point, the more blue we color it. The more probability density it gets from the red point, the more red we color it. But all points always assign some proportion of responsibility, claim some proportion of responsibility for each point, which is computed like this. So here we have the 1D case, where we have these 3 red, green, and blue components, each sort of having some probability density over each of the points. So if we look at this point here, let's say 4.9, we can see that the probability density is the sum of a blue value, a green value, and a red value. And the responsibility of the green point is just the proportion of green in this sum. How much did the green component contribute to this total probability density, which is just a sort of the probability of z given x normalized by the total probability density. So it's like this. So if we do that, so then we have these responsibilities over all the points. So now we can work out how to fit a Gaussian model to this weighted data set. This data set where some points are sort of very important and some points are not important at all. So we have these responsibilities for point I. We're going to fit a normal distribution to this weighted data set, and I'll just give you the intuition and the formulas. I won't work out, they're basically maximum, we'll see later that they're basically maximum likelihood estimators, but I won't work it out entirely. So the first thing we do is we sum over all responsibilities assigned by component I, and that's sort of over the whole data set what proportion component I claims, or the sort of number of points that are claimed by component I. And then we take a weighted mean. Our new mean for component I is just a weighted mean. And we, instead of dividing by n, we divide by ni, because that's sort of the total responsibility that ni claims. The variance is also a weighted mean, so the normal variance is just the mean over this outer product. So instead of taking the proper mean, we take the weighted mean, weighted by the responsibilities. And then the new weight for each component is ni over n. So just the proportion of responsibility it claims. So if one of these components is very far away from the data, it's not claiming a lot of responsibility, so its weight will become very small. So here's a visual explanation. We have these two arbitrarily chosen components again, and we color all the points. These are very blue points because they're very blue, very close to the blue component. Very red points because they're very close to the red component. And then we fit a new blue component to the data, to all of the data, but weighted by how blue the points are. So you see that the component mostly covers the really blue points and doesn't work very hard to cover all the red points, and the same for the red component. And then we recolor everything. It's difficult to see the difference. But the points are now recolored, and we refit the component. And you see a slight shift towards these points here. And as we move too far. And after about 20 iterations, you see that models fit the data quite nicely. So this is the expectation step, coloring the points, and this is the maximization step. Maximize is sort of finding the maximum likelihood fits to these weighted parts of the data. So that's sort of the intuitive way that maximum likelihood works. Sorry, the intuitive way that expectation maximization works. And I'd like to take a little bit of time to look at it a bit more formally. So you might ask why. Isn't this difficult enough already? For these three reasons. Basically, if we formalize this a little bit, we can prove that EM converges. So that's a good thing to know. It converges to a local optimum. So there's no guarantee that you find the global optimum, which if you want the global optimum, you need to work out this sum with a billion terms. But you can at least convert to a local optimum, which in a lot of these data sets is fine. You can also work out this mean variance, these estimators that I showed you, and I sort of tried to do a bit of hand-wavy intuition. You can actually work out that these are the correct solutions. You get some argmax thing that you can rewrite to get these solutions. And one of the things we use in this proof is a decomposition that is going to be very useful later on. In fact, in the next lecture. So let's start there. So this is what we're after, right? The log likelihood of x given the model parameters with this z marginalized out. We're not actually interested in z, but we need it if we want to work this out. So this is the function that we cannot compute. That gives us all this trouble. And it turns out that you can, if you have q, any q function, which is any approximation of the true z given x, which we don't know, that you can rewrite the log likelihood like this. So we basically, this is the function, this is the part that gives us trouble, the thing that we don't know, what the z is given the optimal parameters. Z is given x and the optimal parameters. We approximate that with some function q. Could be a really bad approximation, doesn't matter. And then this log likelihood decomposes into two terms. One is the KL divergence, so the distance between this p and its approximation q. So this term measures how good of an approximation q is for p. And then L is just what's left over. L is not some special function with a special name, or not yet anyway, but that's what's left over after we account for how bad of an approximation q is for p. And this is just the formula for the KL divergence, which we saw in the previous probability lecture, so you can look it up there if you're a little bit fuzzy on it. So it's to prove that this is true and to see what the L function is, it's best to work backwards. Oh, sorry, this is not the KL divergence, this is the L function. So it's best to work backwards. So we're going to prove that this is true by filling in the L function and the KL divergence. So this is the KL divergence, which is the expectation of the logarithm of the first argument with respect to over the second argument. No, sorry, the second argument over the first argument of the KL divergence. And this is the L function that we just wrote. So the first thing we can do is we can take this logarithm. So the logarithm of one thing, divided by another thing is just the logarithm of that thing minus the logarithm of the other thing, right? So if we do that here, we get a logarithm minus qz here and a logarithm minus qz here. And terms of the expectation we can take out of the expectation. So we get the expectation over that thing, expectation over that thing. So these cancel out. So we just reduce it to this. We just get rid of these denominators that way. And then we do the opposite. So since these are two expectations and sums, we can treat expectations as sums. We can work this into one expectation and then work both of these things into the logarithm. So we're going in this direction now. So we get the expectation of the logarithm of this joint distribution over this conditional distribution. Then we rewrite the joint distribution into a joint times this conditional. So this is just a rewriting of this distribution. I think it's slide 22 from the last probability lecture. And now we have two things that cancel out. So this part of the division of the fraction cancels out against the denominator. So we are left with the expectation of the logarithm of x given theta. And this is actually a constant with respect to q. So this is something that doesn't depend on q. Because q only, q is conditional on x, but it only has z as a random variable. So it only gives us an expectation over z, and there's no z in this part. So this is just the logarithm of the likelihood, which is what we wanted to prove, right? We wanted to prove that this thing is equal to this thing plus this thing. So that's the proof. And Q in this case is our distribution on our approximation of the distribution on Z, right? Q is this table of responsibilities that we have, that we say the red component takes a responsibility of 0.1 for point x1. That's our approximation Q to the true value P that we don't know. So now we can show why expectation maximization converges. So let's say we have the log likelihood of the true model or the optimal log likelihood. Let's call that this function. We don't know, whatever it is, but that's the maximum log likelihood we can get with this probability model on this data. And then if we have any other model, any other set of parameters theta, we get something less. In this case, it's quite good because it's quite close, but whatever it is, it'll be less than the optimum, right? For this is just for any arbitrary way we pick these parameters. And then by this decomposition that we've just shown, this falls apart into two parts. The L function of Q and theta, and how good an approximation of Q and P Q is of P. So if Q is a very good approximation of P, then this becomes very small and L becomes very large. And if the approximation is very bad, then the KL divergence takes up most of this value. So now we can redefine or restate the expectation maximization algorithm. In these two steps. So we have the expectation. The expectation says choose the Q given some theta, some arbitrary theta. Choose the Q so that the KL divergence is 0, but keep theta fixed, right? Because this holds for any Q, so we can move Q around and it will keep the length of the bar the same, but it will just move this middle bit around. And we can actually work out what P is for the current theta. So we can actually work out what Q makes the KL divergence 0 if we keep theta fixed. So we can pick a Q that sets this to 0 and then L just covers the entire space. So if we do this, then L stays the same. Then the entire likelihood, the whole length of this bar stays the same. And then in the M step, we do the other way around. So we maximize L, or we choose theta to maximize L, keeping Q fixed. So if we start with this L, we keep Q fixed, and we choose theta to maximize L, then the length of this L bar is going to either stay the same or get bigger. Because either we already have the maximum, we're already at the maximum, and then it stays the same, or there's some other maximum that we can find and it gets bigger. And then on top of that, Q is now no longer a good approximation, might now no longer be the good approximation of P. So because we've changed Q, we also get a little approximation error here, which actually slightly counterintuitively also, but it actually makes our likelihood bigger. And this shows that if we just iterate these EM steps, we're constantly increasing the likelihood. We're constantly, well, at least in the EM step, we're keeping the likelihood the same. And in the M step, we are either increasing it or making it bigger. So that's why EM converges to a local local maximum, sorry. We're maximizing the probability density. And now we can take this M step and work it into a maximization objective. So we want to, the M step is choose theta to maximize L, keep Q fixed. So we want to choose theta to maximize this function, which you can rewrite into this. The QZ doesn't matter because it's we're taking the argmax, so QZ doesn't depend on theta. So this is our maximization objective. And the main thing to take away here is that now we no longer have a sum inside a logarithm. It's disappeared. This logarithm here is not over, even if you fill in the density function of the Gaussian mixture model, there's no longer a sum in the logarithm. So you can find an analytical solution for this, because we've assumed a fixed distribution on these sets. We've completed our model with this Q approximation. We got rid of this sum inside the logarithm, and we can find the derivative and set the derivative equal to 0 and solve it analytically, which will give us these solutions. And I will spare you working that out, mostly because it takes just a little bit more matrix calculus than we're used to. But basically, if you allow me that missing step, you can actually derive these things as maximum likelihood solutions, maximum likelihood estimators for this expectation maximization algorithm. That's the formal treatment. I think we might actually be done a little early today, because I only have one point left, which is what's the point of all this? What's it good for? Well, the first thing is sort of what we already saw. You can use this for clustering. You can look at your data. You can fit a Gaussian mixture model to it, and your Gaussian mixture model will sort of pull your population apart in soft clusters, which you can use for things like customer segmentation or for targeting treatment. If you have a population of people who exercise and who don't exercise and you're a doctor, then it's very useful to say, well, people who exercise can probably take a little bit more of a rough treatment when they're being treated for some kind of disease, for instance. And fraud detection is also very good because you see different behaviors for different people. For instance, within your company, you can see a weird little cluster of people that are only talking to themselves. That's usually a good sign that something weird is happening. So these are sort of very good unsupervised models for exploratory analysis. You do this Gaussian mixture model, you fit this Gaussian mixture model, and then you look at the clusters and you see whether you can interpret it in some way, whether it gives you some information about your data. You can also use it for classification by using this base classifier principle. So you split your data apart by classes and you fit a Gaussian mixture model to each class. And these are very often not, not very normally distributed, like you see here. So here we have two classes. And this is, the data as a whole is pretty normally distributed. But if you split it up by blue and red points, then the normal distributions aren't that good. But if you fit a Gaussian mixture model, you have a lot more freedom to shape your probability distribution along to the data. And once you fitted a Gaussian mixture model to the red class and to the blue class, you can just use this Bayesian principle, this Bayesian classifier principle. You can just, for a new point, check whether the blue class gives it a higher probability density than the red class, and then you classify by the blue class. Just a summary for today. So what we talked about normal distributions, which have a very intimidating formulaic description, but they're actually very useful building blocks that are used a lot in machine learning. Maximum likelihood fitting, which is a good criterion, well, sort of a reasonable criterion. It has there's a lot of things to complain about, but it's a very reasonable criterion for finding a single best model to fit to your data. And it usually ends up, when you do all this mathematics, that you just end up with the sample mean or the sample standard deviation. Then, if we combine multiple of these normal distributions into a single distribution by summing them, we end up with a Gaussian mixture model, which is much more powerful and can take many more shapes. But we don't have an analytical closed form solution for the maximum likelihood fit, which is why we use the expectation maximization algorithm to fit a Gaussian mixture model to our data. It's not specific to Gaussian mixture models. Any hidden variable model you have, you can actually fit this, use this expectation maximization to fit your model to the data. But in practice, it's used most often in combination with a Gaussian mixture model. So that's basically all I had for you. Next lecture, we are going to talk about many things, but amongst others, hidden variable models with neural networks in the middle. So if you have some complicated neural network with an input Z and an output X, you sample a random input Z, then you get a probability model. And the question is, how do you fit that probability model, which has all the power of all these big neural networks, how do you fit that to your data? And that's what we're going to talk about next week on Monday.